Um, Hello again.
Sorry about the technical difficulties and that we had to. This wasn't a live uh, a presentation, but we now that it's a YouTube video, you'll have it for your records whenever you want to see this.
So that means that the people in my club can now go and laugh at me in the future. Yay! Anyways, the Thrive and the destination for mathematics did not move. So we journey on.
So that's for anyone who was at the webinar, but unfortunately could not. Well, none of them could actually. None of you guys could like experience the webinar as we wanted to. So that's just there's the backstory behind that. Anyway, how to math, classical learning methods and real mathematics. Basic, as said previously, you'll be learning a lot of learning styles, how to like get accustomed to math,
Mm-hmm.
not just math. Like you're going to use these learning styles to like adapt to whatever situation you need, whether it still be in school, out of school, in Circle K, whatever.
Or also in the professional workplace, a lot of these kind of techniques in learning can apply to jobs, and maybe if you're like in meetings on how to like absorb information and working with other groups, which we do that in kind of every setting in life.
And of course, this wouldn't be a how to math webinar without a little bit of math. So you'll have a little bit of a taste of what real math will be like. Yeah,
Yeah.
yeah,
Woo.
clearly professional. So as we introduce ourselves, hi, my name is Jared Jimeno. The derpy guy on the right. I am a graduated alumni from UCR. I was a general member, never really got onto board, but I have a lot of experience with math as I guess a current slash former tutor. Everyone want to see it? Okay, let's just say tutor. As a tutor, I have a lot of experience teaching math, learning styles, all the good stuff.
Yeah. And I am Stephanie Garcia. I'm the one on the left with the cool shades. And
Yeah,
I
right.
am a fourth year pure mathematics major at UCR, and I am also the current treasurer for my UCR club. And yeah, that handsome fellow in the middle is Georg Cantor. And for those of you who missed the live webinar, girls took a liking to him.
Yeah, please.
Yes.
That's what I. Yeah, it's me.
Yeah,
Please,
no,
please,
it was Georg. I mean, look at those like mathematical wrinkles. I mean, he's got that like pensive look that girls just really like.
please. Girls are obviously all over me.
Uh-huh.
Please.
Mhm.
Also, shout out to anyone who can figure out the show we're referencing.
Yeah, leave it in the comments below because now we can do that. Anyway.
Oh, they can still do that.
What?
The webinar, they can still do that.
Oh yeah, but now below. Now they were in the
Now it's
side.
like to the bottom left. Now it's just
Okay.
below. Okay, back off topic. Continuing. We'll start with some introductions
Yeah.
more about math, how it relates to Circle K.
And then some general misconceptions about math, or like all the biases that people have towards math that aren't true or that we hope to change today.
Also, we have this one be again a math webinar without a bit of a math lesson. So we'll give you a perspective on math that you probably haven't seen. And then I guess we'll move into some learning stuff, like learning styles, how to like learn in school, out of school, how to get used to that type of stuff.
And then we'll have a little break time and watch a video. Actually,
Yeah.
no, we'll just link.
No. See the YouTube video, right? Trust me, you'll see the video.
Okay then.
You'll see the video. Like it'll be YouTube within a YouTube.
Oh, YouTubeception,
There
guys.
you go.
YouTubeception.
We'll go back to learning styles. We'll finish that part off, and then I guess some arbitrary amount of things to do later. We'll go end up with a proof.
Woo.
Proof.
Woo.
It is fun. I swear it's fun. Okay. So first off, this webinar, I guess, YouTube video presentation now. It's not office hours. You please do not come. Well, you could. I guess now you could probably comment down below about how to do your math homework,
True.
or just message one of us. Me, sorry. Sorry. Message me, Jarrett. Message Jarrett if you want help with math.
I'm still living that midterm life, y'all.
Um, Also, we're not going to split your restaurant bill. There are way too many people like how to do it. Oh, I only have card. Oh, I only have a 20. Yeah, please. It's not that bad. Please don't make us split your restaurant bill. And obviously, we're not doing it. We're not going to specifically how to do math in this specific webinar. Again, message us, me.
Or I mean, you're on YouTube, so go find other videos on how to help you do your math homework. There are tons. So.
Okay.
Yeah. Next slide.
So how does this all relate to Circle K? Well, I want to say for the exception of me and some very few people that graduated in the middle of the school year, we're still students, right? You need to do math in order to pass certain classes, and basically, we wouldn't want you failing a particular class just so you couldn't go out and do service or anything else related to Circle K.
Oh, and of course, we're going to be teaching you guys some problem-solving skills that aren't just like in math, because of course that's what we do in math. But they can also be used in Circle K because a lot of us are general members and some of us are chairs or board members or family heads, and problem solving is kind of just a good tool to always have because you never know what could, like, something goes wrong and you need to be quick on your feet and have come up with a lot of solutions, and it's something that is it's just really useful to have as any kind of leadership position and also in other kind of walks of life. Yeah.
Then we also, with analytical thinking, it's more of a, you get used to trying to figure out what situation you're in, right? What applies. Like, let's say you're a chair and you're trying to figure out, oh, so how are I going to maximize the number of, like, minimize the number of cars for the maximum number of like, club attendees for a certain event, right? So it's like, so you have to know how many cards you have, how many members you got. You have to know where they're going. There's a lot of things just like to understand your situations. And it goes back to problem solving.
Yeah. Also, trial and error. Whenever in math we use this a lot, especially when you get to the more theoretical aspects of mathematics. There's a lot of trial and error, and you just kind of have to try different things and see if it works. And for the most part, it doesn't really work. And then you finally get to one little solution that actually works. And that's kind of how you can see some problems in Circle K too. That sometimes you just really don't know what to do, but then the little idea comes up, and it's just about trying stuff out. And no one really has it right, so. A lot of trial and error.
Well, and also, when you don't really know what to do and you've tried a billion different things, eventually you're gonna have to learn to think outside the box.
Mm-hmm.
Where, like, it'll hopefully work and you pray it works, and just like you go through the scenarios, and sometimes you gotta just be different, right? So let's say you're trying to do a different fundraiser, right? You'd have to be creative with like how you approach things, just so you can have something that's different, something fresh, right? So hopefully, like all those things will help you in your Circle K time.
Yeah. Next slide.
Okay.
Okay. So there's common misconceptions, or what I like to call math biases. First of all, math is not applicable to our everyday lives. I hear a lot of people say this, that like, when are we ever gonna use math? Like, when am I gonna need to use this? And yes, there's like a lot of stuff that like maybe you might not be like driving equations on a day-to-day basis, but there's a lot of like the thoughts that we mentioned in the previous slide, that there's these tools that you can use every single day, and all these problem-solving skills and thinking on your feet, and these things you can apply everywhere. So it's more about how your mind works and how your mind gets used to kind of thinking on its feet that is applicable every day. And then math is all about numbers. Well, as a now fourth year pure math major, I don't really see a lot of numbers, and it's kind of like really cool when I see one number. I'm like, oh, there you are, friend. I forgot about you. Like, there's a 2. And so, yeah, you actually don't see that many numbers. When I do see numbers, it's like, yay, I get to like do stuff. But now it's no. I see zeros. A lot of zeros.
Also, in this presentation, we'll also be like we'll also try to use as few numbers as possible, just to see that just so you can see that math isn't all about numbers.
Yeah. And if another one that we hear a lot is if you don't understand math, you never will. And I guess it's kind of like, you take that one course that's like so difficult, and you're like, I don't get this. Like, I'm done with math. Flip the table. And it's just like, you never know. Sometimes there's some different types of learning that we're going to be teaching you today, and some of those might actually make you see math in a different way. You'll actually start understanding some of it, and maybe you'll change your mind, and we hope to do so today. And since you don't like math because you don't get it, and I think this is kind of just like a universal thing. It's that a lot of people say kind of like, I don't get all this calculus stuff. I don't get it. I don't like you. But today we're gonna teach you a lot of stuff that hopefully you do understand math, and maybe you'll like some concepts. Maybe hearing it different ways or learning it different ways you might actually find something that you like about it. And math is boring.
Well, I like math, so forget you guys.
Yeah, we're pretty cool. We're pretty cool.
And if you're saying that math is boring and we think math is cool, do you think we're boring?
Yeah.
Please don't.
It was like done, like proof, like lawyered. So done. Next slide.
Please don't call us boring. So, what I think of the true beauty, like the true nature, the true beauty of math, it isn't really what you learn about in high school and like all middle school and elementary school. What I've noticed when I was like tutoring kids, college, high school, all levels, that especially in K through 12, it was more of a know how to do things, right? Understand like the basic mechanics of how to do it. On the side, there might be a bit of problem solving, but it's more like understand this function, understand how it works. Um, and you really do get to the problem solving when you hit college, when college level math. And that's what I've thought. If you compare it to like say if you take it in an art class, right? Maybe they'll teach you how to paint a fence or a sheep or something, right? And that's all you're gonna learn how to do using basic basic art styles, and you progress that way, like how to be a quote unquote artist if you know how to use all these art styles. But then I have friends, and I've seen a lot of like artworks where people just doodle, and they like to experiment. They like to just see what works, see what doesn't work, and hopefully, and then they progress that way. See what they like, what they don't like, and and as they progress, it becomes a more and more beautiful piece, just like math. And lastly, with the beauty in math, the set of rules, right? There's there's like, usually you just set a rule of like y is equal to x squared, right? But it's more complex than that. Sometimes you can think of like take this piece of paper, fold it in half, and do it again, and do it again, and do it again, and then you get this, I guess, this fractal to some, I guess, some mathematicians look like a dragon, right? Just by folding a piece of paper in half. There's also like ratios. There's a lot of other things if you just like set a rule and you just like let it happen. Uh, Rules that are probably a lot more complex than y equal to x squared. And then also like you don't have to see math in just a classroom where it applies. Nature for some reason likes to use these mathematical equations. One of them just uses a three dimensional sine wave. A lot of nature likes to use the golden ratio. For some reason, it just happens the way it does. If you look at the shell, right, you can see how it spirals out through this particular rectangle. If you look at the picture on the right, you see the golden ratio, and the golden ratio happens a lot, like in a lot of the proportions of man, from the height of the navel, from toe to navel, the navel to the rest of the head. That's the golden ratio. If you, there's also a lot of other ratios in the face, the arms, the eyes, the ears. There is a lot. Trust me about that. It's an art. If you've seen the Mona Lisa, there's this proportion to her, and it just so happens to fit the golden ratio. again. And if you look at the painting on the Sistine Chapel, you can see that the ratio between Adam and his finger, and then you can see God to his finger, right? It also seems to be this golden ratio as well. It's aesthetically pleasing, and then for some reason, someone, or I guess a bunch of people figured out this is the proportion that just works, that looks good. And finally, it's the language of the universe, right? We use all these equations to understand how like winds and electric fields, or even how the cosmos forms. And even, I mean, in the bottom corner, there's more golden ratio if you haven't noticed. Um, did you want to say something about the language of it being the language of the universe, Stephanie?
Good.
No. Oh, okay. It was more about like math literacy and about.
Oh, yeah. Well, what's it called? One of the things that kind of motivated us to do this webinar was because, as you all know, the DSI this year is Leaping for Literacy, and one of the things that have been overshadowed is, of course, mathematics. And I think I've heard like a lot of people saying that, like, we can't do math. Math isn't literacy and stuff like that. And I'm like, like people need to learn math too. It's language. It's a way of thinking, and it has its own kind of like cute little shortcuts if you ever get higher up in mathematics, and yeah, it's just a good way to communicate.
Okay.
Good way to think.
Well, speaking of math literacy, it brings us into our next topic, and we're gonna start you out with some problem solving, how to read these problems, how to like understand how to do them. So, Stephanie, if you could explain this problem to us.
Okay, so of course, here we go into like actual terms. Okay, so question says, find the cardinality of these sets. So of course we're all like, what does cardinality mean? And
Oh, well.
yeah, okay. So we're gonna put it in layman's terms. A set, which is those things in those cool brackets, is a group of things, and so that's pretty simple, I think. And cardinality is the number of things in a set. So, can you guys tell us what is the cardinality of the set on the left? I feel like Dora.
Right? So did you? All right, Dora, say it again.
It's like, do you know what the cardinality of the set on the left is?
And you can also do it on the set on the right.
There we go. And so.
Yeah.
Woo.
Okay.
Okay.
All right,
and
enough
so,
Dora the Explorer. Are you done with this slide?
Oh, okay. Well, for all of those wondering, there are actually 4 things in the set on the left. 1, 2, 3, 4. So the cardinality is 4. And on the right, the numbers are 2, 43, and 9.2.
Sorry about that last comma.
The comma got like, I wanted it to be free, you guys. Anyway, so there's 3 items. So the cardinality is 3.
And again, the definition says group of things or number of things, right? We don't have to limit ourselves to just numbers, right? Let's try another example.
Woo.
Try this one. Find the cardinality of this set of an apple, a cherry, some coffee, a laptop, pie, Superman, Pikachu, a cat, and a BuzzFeed video.
Oh, okay.
So you can go ahead and try to figure out the cardinality of that. Comment that.
Comment below, you guys. Ooh, interactive.
Okay. And so you might be wondering, well, what about if we put all the counting numbers in the set, like 1, 2, 3, 4, 5? Right. What about that? Well, technically speaking, it is infinite, and it's still countable at the same time. And we're not talking just about Chuck Norris counting to infinity twice. It gets very philosophical. I believe it was Plato that mentioned that if you had all the time in the world or all the time in the universe, then you could count all the countable numbers, all the natural numbers. You will see more about this later.
Okay.
But then, in a cool way, let's say sets were like infinite, right? There would be a decent way there should be a way to count them other than just like you don't have like 1 to 2 to 3. We don't have all the time in the world. So a lot of times, what we like to do is compare it to other sets. other sets we know, and then we know the cardinality of that, and we can just compare the two, right? So let's say we had these two sets, right? And let's say they were infinite. So you can see you can see that as long as we can draw a line from one element, one thing in one set to the next, we can see that it it's just so happens that we can count if we know what the cardinality in set one, we can find the cardinality in set two, and you can clearly see that one of these sets is bigger by than the other just because there's an element that you just kind of left by itself.
Mako is left alone.
Yeah.
Yeah. But see, it kind of makes like counting kind of more basic than just numbers at this point, because it goes down to if you can match it up to another thing in another set, you not only know if they have the same amount, but you can tell which ones have greater amount of objects than the other set. So you don't have to know this set has 10 things and the other set has 11. You just have to know if I can match them up, then I know that one set is clearly bigger than the other.
Okay, so and usually if it's a more organized structure than this, we can find a rule. We can find a relationship. A relationship. We can find a relationship between the two sets, and it's what we typically call functions. So, is there a relationship? So we can just take a basic table. Here we already know the relationship. It's 2x minus 7. We can take one thing in one set, being 2, and we send it all the way to, we match it up with the 11 in the other set, and it goes on, right? And this is where these numbers go to. So I think we have another example.
Yeah.
What's the relationship here? If we were to call this x, and we were to call this y, what would the relationship be, right? And you guys should know what it is. It's 2x, and the dots just mean they go on forever like this.
So I guess in these two sets, they can go off to infinity, but we know that they're the same size because we can make a one-to-one correspondence.
Know that word, one-to-one correspondence. Okay, so moving on.
Yeah.
Now we actually move on to the learning styles. It's more of a, if you don't quite understand math, if you can at least understand these styles, you'll definitely be able to, what's the word? Really at least understand math a bit better. Hopefully, and if not, you still have these learning styles to use in your everyday life. The model that we're going to talk about in this presentation is the VARC model. It has to deal with learning with your senses, like if you can touch or see or hear, like that's the sense that you like. That's how you're going to learn best. And there are other models too. We'll mention that at the end of the video, and there will be links in the description about that.
Yeah.
First of all, like, you do want to find out what you're comfortable with, but at the same time, you want to be able to learn all the styles and just at least understand them a bit. It's like, would you really want to learn how to drive a car, but only about reading about it or watching videos, not actually like getting behind the wheel and just driving, right? And it kind of gives some description to the picture on the right.
Yeah.
And
at least for me, I'm currently learning another language, and I find myself using different methods and implementing them at like different times in my learning process. So for me, I like reading the material first, and that's how I kind of get my like first start off of everything. And then at the end, though, when I'm actually like reproducing, on like exams, kind of talking it slightly, like kind of like with that auditory, kind of helps a lot, and it makes me form connections between like English and the other language, and it kind of just comes full circle. So it's not just about learning one method and how that works for you. It's about learning all of them and knowing when to use them and combining them.
Honestly, in terms of math, you're going to be learning a lot of different. You probably would need to use all those different styles just because maybe you need to like get a feel for it just to know, let's say, a theorem. But then you would have to like, if you want to like just learn the concept like during class, like, you probably will want an audio or a visual type of learning. So it all does, again, comes around full circle. Starting off, we have visual learning, right? We like to see the big picture. And I've noticed that like visual learners will simplify the problem to something they can just like draw on a board. And personally, for me, I like drawing on whiteboards and blackboards, so because you just see everything, and I love it.
I know for me, learning geometry was a lot easier through pictures, even if it's like some kind of like upper division geometry level. Like having those cute little triangles and stuff, they definitely helped a lot more, and it was a good way to kind of learn the concepts first and then later apply them through a different method.
Right. Moving on, we have auditory learning, right? So you like to hear the ideas, like hear the ideas out. You like to like just keep talking, just like you learn just by listening. What I've learned that study groups are very helpful because you get to pass around ideas.
Yeah.
Talk to your professor or teacher in like in lecture during lecture office hours. Sometimes you just like the atmosphere of a lecture, so you can record it. I've known professors that personally do not want you to record, but it happens. See if you can just ask. You never know. Also, you can be like me and just like mouth it quietly
Yeah.
because if you're around people and you start talking to yourself, you kind of look weird. At least in my opinion, I've gotten that a lot. But if it helps you, you should forget them. Just
Yeah.
do what you need to do.
Math is cool, guys. So.
Any
They're
plans?
just jealous. Oh, yeah. I know for a lot of us, sometimes we don't understand the way some teacher explains something, and one of the like benefits of auditory learning is that you can hear it in maybe concepts explained in a different way. So maybe one definition didn't work for you, but explaining it a different way can work. And yeah, that's how you learn. And you get, especially like when you work with groups, you kind of get to see how people are kind of piecing everything together too. And if you didn't have it pieced together, maybe a combination of theirs or one of their ideas or how they're using it to, like, how they're kind of working everything out in their heads might appeal to you.
Okay. So, I guess this is the part where we take a break.
Oh, break time.
So in learning, right? Like it's helpful to take a break from class, just to just get the mind fresh. But let's get back to the learning. In terms of learning styles. More about reading and writing, right? So you learn just through reading about it, right? Like writing it down, like that's how you get a feel for it. I've noticed a lot, like writing flashcards definitely helped me with things for reading and writing. I remember in my ethnic studies class where the exams were very based off all like just definitions, right? I would just take flashcards and write the definition, like the word, the definition on the other side, and I've honestly learned more as I was writing the definitions themselves than I had my friend actually write it for me. And the ones I actually memorized were the ones I wrote down myself. Basically, it.
Yeah, I think so. Like I use that for both math, like when it comes to like calculus, and you have to remember all those formulas, or like those trig identities that you like they expect you to remember once and then remember like recall it like a million times. Those are always good to have on flashcards. Or for me, like for when you're taking Spanish or another language, writing conjugations down, having those on flashcards helps a lot because you can just kind of like how Jarrett said, like just writing it down alone like helps. So it's kind of you start memorizing it just by writing it down.
Also, this also falls into like writing, writing notes, right? And we'll go on to that. In particular in math class, right? You'll see an example in your notebook and you'll write it down, right? This is exactly what the teacher wrote down, and this is what it is. I'm like, well, and you go like a few days later, maybe a week later, you go back and read the notes, like, what in the world did I just write? Like you have no idea what in the world you wrote. So
every day in math.
so a lot of times it's good to help annotate your notes, something to just explain it as so it's good for reference later on. The popular style would be use Cornell notes, right? So
Mhm.
you take a you make a huge margin and you write the notes about your notes on the side. Um, Sometimes that'll work.
Yeah.
Personally, for me, what I like to do is just like forget the extra margin and just kind of like right next to it. All right, so maybe you have some snarky comments about the example, or maybe you want to give yourself a reminder. Um, Definitely don't make your notes boring, or at least boring in what you think is boring. Personalize it. Have fun with your notes. Have fun with the class. Have fun with math. Definitely. Um,
I think I used a lot of color coding. Color coding helped, or like boxing all the important things. Like for me, like I see a lot of definitions and theorems. I think that shows up in some classes that y'all are taking, and I think boxing them is always like, oh, that's the important stuff. So that's always good, and using different color coded stuff so you can like write your notes, or maybe the comments that like the professor said, like, oh, by the way, this is from theorem 6.7. Don't forget this. If you're looking back at this, don't be like, where did he pull that out of? He pulled it from before. And so that's when a different colored pen could come in handy.
Yeah.
Yeah.
Okay. Well, and finally, there's the kinesthetic learning where you just kind of get your hands dirty, like right, learning to drive, learning to ride a bike. Uh, in terms of math, it's a lot of practice. It's a lot of repetition. It's just like working on your homework just to see get a feel for the theorems. But then like this is the part where you could get stuff wrong, right? Because with homework, you're gonna keep doing it over and over and over again, but maybe you'll do it wrong. This is the time where you have time to learn how to get it right.
Yeah. That's you kind of start to learn this way what you're doing wrong in the first place. Like if you sometimes you memorize all these definitions and then you realize you actually don't know how to apply them, or all the stuff that the teacher's like, yeah, I got it. Number 1 + 1 = 2. Like, yeah, it all makes sense. But then when you actually start doing it, you're like, wait, what is 1 + 1? Oh no. And then that's when you learn, and then you can figure out what you need to work on. And of course, once you got it like down, like you can do it in your sleep. Like you're good to go.
Also, shout out to the math majors who know how to prove 1 + 1.
Whoa. Woo woo.
Yeah, it gets mind blowing.
It does.
Huh. So the last part I want to talk about learning is kind of like learning how to boost your brain activity. And it's not so much about like eating properly. It's more like asking the right kinds of questions, right?
Mhm.
Sometimes I can ask you to like, all right, state the definition of such and such, right? That's or what's plug in 2 into x² + 5, right? That's basically, could you recall what to do? Basic standard operations. That's more of like a high school math, middle school math, and just some math definitions you see in college. Uh, Moving up the ladder of what this is called Bloom's taxonomy, by the way. Moving up the ladder, you have application and analysis. So that's more of a you're breaking it down, thinking about what to do with this problem. Let's say you had to learn chain rule. I've seen a lot of people have trouble with chain rule, and it's like, and I tell my students, okay, so how do you approach the problem? Like, what do you know about chain rule? What do you need to know about it, and that type of stuff. And so that's definitely more of a college calculus type thing. And finally, we go up to the top, and it's evaluation synthesis. Like, this is more of a getting that creative, like unconventional thinking to use in math, and just like learning to prove a theorem. So this is more of a like math in the sense that in terms of proofs, I'd like to say.
Yeah.
But what's important is like one, you start from the bottom, right? You have to know these. Okay, we're not gonna go there, but you have to know these. You have to know some base stuff, right, before you can really like work on like the higher level types of math. And honestly, Bloom's taxonomy isn't just for math. It also applies to other subjects. It applies to chemistry. It applies to physics. It applies to English, history. Um, Sometimes like you want to like in the higher up levels, you want to make a thesis, or you want to make an opinion based off like what you've seen, what you know about life, and you can back these things up.
Oh, go ahead. Oh, okay. Yeah. So I guess kind of what we see now that we've taken all these like tons and tons of math classes is that kind of how this like whole pyramid works into like our field. And in the beginning, you learn all these definitions, and then you do the whole plug and chug kind of thing, and then you actually start like applying them when you get to calculus, and then like right when you think you've got it all figured out, you're like, our professor says like basically like, let's just stop. Let's see why we can even use these formulas, and then we're like, oh no, what's gonna happen? And that's when we kind of just relearn mathematics as a whole. And so, yeah, I guess that's kind of when you start to like evaluate what is math. And then we learn, what does zero actually mean? What does it mean for a set to not have anything in it? And yeah, so these things can also be not just math in life too. I mean, in once you get to like the end of math, you kind of learn how to put all these pieces together and use what you've learned in the past to kind of like come up with like new kind of groundbreaking ideas. And it's kind of what you use in life too. Whenever you're trying to like figure something out, you use kind of prior knowledge, and then you kind of arrive at conclusions based on that.
Well, hopefully this part of the learning styles helps you like understand math, because we're gonna go back to math, right? And it's kind of we're gonna do a proof.
Woo, woo.
Where I bet you can count all the rational numbers, basically all the fractions in the world that exists.
Oh.
You can count them.
Yeah. So if you guys don't remember what rational numbers are, they were always at like that set with the Q. Yeah, I hope you got And they were like,
I'm pretty sure none of the not math majors know, but yeah, that's basically what they are. It's a Q.
Yeah, it's a Q, or like fractions. So like rationals are actually called rationals because they are ratios of whole numbers. So they're like a whole number on top of another whole number, and where the bottom one isn't zero, because of course we can't divide by zero. That's like the one rule, you guys. And so our friend Georg Cantor is back, and he's the one that showed that rational numbers, that the set containing rational numbers is actually just as big as the set containing natural numbers. And like we said before, the set of natural numbers is infinite. Woo! But it's still countable.
Right. So in this example, in this proof, we're gonna just assume that we're all Chuck Norris, right? And we can count to infinity twice, 3 times, however many Chuck Norris counted to infinity.
There we go.
All right, and then
that's easy, guys. like totally. Let's just like.
Okay, but then here's the proof.
Okay, so here's what we're gonna do. So these are all rational numbers, of course, fractions, and so we're gonna line it up like so. Okay, yeah. So we have like we're gonna order them where all like it's kind of like a grid, and so there's gonna be the 1/1 and the 1/2. So the 1 is on the numerator all across the top. So from left to right, the numerator will stay the same, and from top to bottom, the denominator will stay the same. And for those of you noobs, the numerator is the number on the top, and the denominator is the number on the bottom.
Right.
And
well, keep going. Sorry.
Oh, okay. And so this is how we're gonna kind of show that the set of rational numbers is equal to the set of natural numbers, or whole numbers, yeah. And so here's what's called, one of the things that we showed you guys before is the one-to-one correspondence. So we have to be able to pair them up, kind of like how we did with the whole sets with the little lines. And this is going to help us do that, because we can't just be like, how do you write down every single rational number? Like, whoa, how do we do that? And this is how we do that.
So basically, what we do is the matching numbers, right? So 1/1 will be matched with the number 1, right? Then we go to 1/2, and that will be matched with the number 2. And you could try to go this way, right? Just go to 3, then 4, then 5. But what you notice is, like, as you go along, you go off into infinity.
Yeah.
But the thing is, you don't know where that ends, so that's kind of where it stops.
Yeah.
Likewise, if you tried going down this way counting, you're still going to run to infinity. That's still a big issue. So what Cantor did, right? Instead of just going left to right, why don't we go diagonally? So we'll take 1/1 as lined up with number 1, and then this one will go to number 2. But then we'll go to 2/1 for number 3.
Yeah.
Go down for number 4. And then we're gonna obviously skip 2/2 because it has the same value of 1/1. So we skip over, and this one becomes 5, then 6, then 7, then 8, then 9, then 10, and again you skip whatever you don't use, and so on, all the way until you. And this works because as you go to a diagonal, you hit a physical countable wall.
Yeah.
that you're gonna have to turn around and just like loop back and forth. So it seems to work. That this is the way you're gonna prove that all fractions are countable.
Yeah. 'Cause now we found a cool, nifty way to make a list out of these numbers, and of course, since we can list the natural numbers, we can make a kind of one-to-one just by counting it.
Hence you can count to infinity. Hence your Chuck Norris. There you go. I bet Chuck Norris couldn't count fractions. Maybe. The joke is old. It's back like high school for me, and I graduated college. Maybe if we could take this, maybe we can count all the real numbers, all the little decimal places. That you never know.
I wonder.
But we'll leave that for you.
Questions.
We'll leave that for you guys to figure out. And if you're watching this before DCon 2015, maybe you could tell us at DCon 2015.
Yeah, there we go.
Which you guys should go to if you're in Circle K.
We'll see you guys there.
If you have any questions, comments, concerns, definitely comment below. But yeah, comment below.
Yeah.
Comment your math homework problems. If you see us try to come back to this video like a year later.
Yeah. Maybe you think math is cool now. So we'd like to hear that. There we go.
Also, thank you so much for watching. We left a lot of links down below about supplemental links.
I think we'll add them to the info box then, because they can't actually.
The description.
Oh yeah, we could always hyperlink. We'll figure it out.
Yeah, the description's below. Yeah.
There we go. We'll put it on the description below. Some kind of cool videos.
YouTube channels.
Yeah.
We have a couple quizzes if you want to figure out your learning styles based off the models.
Yeah, lots of fun stuff.
All right.
Ooh.
Cool. All right. Thanks for watching, guys.